A lens-based camera is a lot like the pinhole camera in the sense that we are trying to record an image on a screen from a distant object. But now we're going to use the advantage of a lens to collect a lot more light than the pinhole would allow us to do. In a lens-based camera, a lot of different rays from a distant object, for example the man's pipe in this picture, head off in different directions. But the lens is going to try to collect that light and send it all to one place so we can take the picture faster. The lens diverts rays heading in different directions to a single spot on the screen. What's shown here are the rays coming from his pipe, and they all head to a unique place on the screen, even though they were heading off in different directions. The same would be true for the rays coming from his jacket. They would all, from the tip of his jacket, they would all head off in different directions and go to a unique place on the screen. Thus, the lens-based camera is a little bit more efficient in the sense that it makes use of all the light rays heading off in different directions as long as they hit the lens. It doesn't just have to hit the pinhole. All of these light rays contribute to the image spot. The photograph here of this farmhouse is taken with a lens-based camera and is taken much more quickly than would be with a pinhole. Now we don't have to wait 30 seconds for an exposure like I did with my pinhole camera in my kitchen. Rather, you can take exposures that are a 20th of a second, or a 30th of a second, or maybe even the 1,000th of a second, so quick that actually we can capture in still motion a person that's running across the room. A camera consists of several pieces. They always have a lens at the front, and the lens directs incident light from a distant object onto a screen. The screen is located at the image distance from the lens, so that the image can be traced or recorded on film or a CCD. The gray region here is showing you light coming from the distant object that actually gets captured by the lens. What's important to recognize, however, is that this represents the envelope of all light that reaches the screen. It doesn't actually show you the path of one particular light ray. Because again, if we think about the light coming from the top of this tree, it's heading off in different directions and hitting the lens at different spots. All of those light rays are directed to one spot on the screen, and that's upside down, of course. Likewise, if we think about all the light rays that come from the base of the tree, they head off in different directions, and then they are all directed to one single spot on the screen. So the waist, or the narrow part of that gray shadow, actually shows us where the focal point was. And notice that the image is not located at the focal point. The image is located in the image plane. It's the place where the image is created, and we have to use that 1 over p plus 1 over I equals 1 over f, a formula to calculate where the image distance would be. The image point is actually at the back where the film is, not where the focal point is. Not necessarily, anyway. Sometimes we know that image point distance and focal length can be the same, but that's not necessarily the case. But we do have to have the film be at the location of the image, or otherwise we won't get anything but a blurry mess on the film.